Yeah, it starts with A. ATP, yeah, let's not make this too hard. So the ATP, right, ATP from the mitochondria and ATP equivalents can be transferred to the cytoplasm. So ATP, right, the high ATP from fatty acid oxidation affects the equilibrium of this reaction, pushing it this way, which, since that's going to make the 3-phosphoglycerate low, that's sort of, right, you're making phosphoenol pyruvate, you're keeping 3-phosphoglycerate low by the high ATP, pushing this equilibrium this way. That tends to draw everything up through gluconeogenesis. Now we've got lots of 1,3-bisphosphoglycerate. We've got NADH being shuttled out here. That tends to push everything to here. Now we've got lots of glyceraldehyde 3-phosphate. It is in equilibrium with dihydroxyacetone phosphate, so some of it ends up over here. Enolase, or aldolase, combines it into fructose 1,6-bisphosphate. So from here to here, we're just setting up high phosphoenol pyruvate, high ATP, high NADH. That trio, lots of this, lots of that, lots of that, tends to push all these equilibrium reactions up to make fructose 1,6-bisphosphate. Okay? What's the matter, Robbie?
She's asking the last one. That pushes.
Say that again?
She's asking what was the last substrate that pushes.
Well, you've got phosphoenol pyruvate, ATP, NADH. ATP and NADH are coming from fatty acid oxidation or possibly amino acid oxidation, right, in the liver. So these equilibrium reactions are pushed up to here until we get, right, this bottleneck step. And so our sort of exit step from standard gluconeogenesis is the fructose 1,6-bisphosphatase. And when we get to the fructose 1,6-bisphosphatase, we end up back at this figure, right? The one we talked about. We talked about the control of phosphofructokinase in this direction. Now we're going to talk about the fructose bisphosphatase in this direction. So here's our fructose 1,6-bisphosphate. The fructose bisphosphatase just catalyzes the simple hydrolysis of this ester to make the alcohol. So the water is directed to attack, I believe it attacks here with phosphate as the leaving group. So I'd have to look that up to be sure. Energetically that would make more sense, but enzymes don't always have to follow those rules. So in this case, the fructose bisphosphatase is inhibited by AMP. Does that make sense?
Yes.
How, Melanie?
Because if you have AMP, then you're doing glycolysis.
Right.
Like you're
if you have
using
AMP, you need to be doing glycolysis, not gluconeogenesis. So AMP was activating glycolysis. It inhibits gluconeogenesis. So that makes these two steps responsive to the current metabolic environment, right? Fructose 2,6-bisphosphate that we talked about with glycolysis inhibits fructose bisphosphatase, right? Well, it activated glycolysis. Let's see. We made fructose 2,6-bisphosphate in the liver in response to we made fructose 2,6-bisphosphate at rest. In response to glucagon, we broke down fructose 2,6-bisphosphate. So that in response to glucagon, we unactivated glycolysis. We uninhibit fructose bisphosphatase. And so in response to glucagon, we promote gluconeogenesis in the liver. That all makes sense? Elizabeth is thinking. Okay, just to get it on the record, I want to move forward. We've done that before. I want to move forward and talk about this last step. I'm going to move up here. This only occurs in the liver, right? The liver is the only tissue that once we're at fructose 6-phosphate and glucose 6-phosphate, this hexose phosphate pool, the liver can dephosphorylate glucose 6-phosphate to make free glucose for export. But that occurs in the mitochondria. Right? That dephosphorylation occurs in liver mitochondria. So liver have a multiple protein system. One, they have a glucose 6-phosphate phosphate ion antiporter. So glucose 6-phosphate goes in, phosphate ion comes out. So there's a glucose 6-phosphate phosphate ion antiporter in the mitochondrial inner membrane. So since an organic phosphate and a phosphate ion are going in and out, that mostly addresses the charge balance. Right? That's why we do the antiport. Gets glucose 6-phosphate into the endoplasmic reticulum. Within the endoplasmic reticulum of the liver cells, there is a glucose 6-phosphatase, which hydrolyzes the phosphate from glucose 6-phosphate, makes free glucose. Also in liver mitochondria is another member of the GLUT transporter family. I can't remember which one it is. If you go back to my original figure on the GLUT transporter family, it's on there. Might be GLUT 6, one of those. Right? So, glucose then can be transported back out into the cytoplasm. As glucose concentration rises in the cytoplasm, free glucose is a substrate for the plasma membrane glucose transporter, and so free glucose can escape the liver cell through the GLUT1 and GLUT2 in liver cells. Yeah.
Why? So wait, the glucose 6-phosphatase, that's in the ER?
That's in the ER.
How did it get from the mitochondria to the ER?
The glucose 6-phosphatase?
No, the glucose 6-phosphate. That you're messing, because you
It's-
brought it into to the mitochondria,
No,
right?
no. We're in the cytoplasm here.
Right, but then you bring it. The antiporter is
Into
in.
the endoplasmic reticulum.
Oh.
Did I say mitochondria?
Yeah.
Oh, I'm sorry.
And I was
No,
like,
into the endoplasmic reticulum. It says ER.
Just kept saying
so it's in
Did I say?
liver.
I'm sorry.
It's in liver ER, not mitochondria.
Yes, liver endoplasmic reticulum.
Okay.
Okay, whoever watches this online is going to be really confused. Right? So, yes, the antiporter is in liver
ER.
endoplasmic reticulum. Did
Okay.
I really say mitochondria all
Yes.
those times? I'm sorry. Liver endoplasmic reticulum. Glucose 6-phosphate gets into the endoplasmic reticulum. It is dephosphorylated. The free glucose can escape because there is also a member of the GLUT transporter family in the liver endoplasmic reticulum. Did I say it right that time? Meaning there's now free glucose in the cytoplasm. That free glucose in the cytoplasm is a substrate for the plasma membrane glucose transporter in the liver, either GLUT1 or GLUT2, so that glucose can escape to raise blood sugar. And I got all that in time before the end of the hour. So now all of gluconeogenesis is in play for the test, and you can ask me questions about it on Wednesday. And you didn't think I was going to get there before the test. So we got all of glycolysis, all of gluconeogenesis, because I'm going to go back to the beginning of glycolysis, even though we had a little bit of glycolysis on the last test.
Oh.
So now things will go faster. We've established some sort of ground rules, so now things will go faster when we talk about other systems. We won't have to spend quite as much time laying the fundamental theoretical groundwork that we had to with glycolysis.
Do you ever take home exam?
I do. She asked,